4.4 optimization part 3. We're going to do problem number 21 in the book. I have drawn some pictures and oops. And I have a bunch of stuff here. So I want to go ahead and explain what the problem says. A boat on the ocean is 4 miles from the nearest point on a straight shoreline. The point is 6 miles from a restaurant on the shore. A woman plans to row the boat straight to a point on the shore and then walk along the shore to the restaurant. So I drew a picture. We have that ready to go. And notice I have that the total distance from the point on the shore that's the nearest, remember the shortest distance between 2 points is a straight line. And the restaurant, this is 6, so I'm going to call this part of the triangle x and the rest 6 minus x. So then I want to go ahead, and it says here, if she walks at 3 miles per hour and rows at 2 miles per hour, which I have that data down, at which point on the shore should she land to minimize the total travel time? So basically, I'm going to use a couple of different equations. I have an equation for how she's going to row. And what I did is set up another triangle. Remember, this is going to be r, and our hypotenuse of the triangle. So I have that. I'm going to use Pythagorean theorem, solve for r. So when she rows, it's going to be a distance of the square root. We have there. And then the next part is where she's going to want to walk, which is this part of this equation. She's going to walk a distance of 6 minus x. These two equations are the D part of a rate problem. So I have here, we're going to use that. We know distance equals rate times time, but this is because we want to minimize time. We're going to solve for t. So this is what our type of equation should look like. So I did a capital T for our equation, and I had the distance, so this is really d over the rate for her when she's rowing. The distance is the square root. The rate she was rowing was 2 miles per hour. And then this, we're going to add it to the distance of what she would have to walk over the rate of how fast she walks. So this is my equation that I want to go ahead and take the derivative of. So I went ahead and took the derivative of this one. And I said that we have two individual terms, and I took the derivative of each. But before I set it equal to 0, I want to go ahead and make it one rational expression. So I take the denominator, and I make sure I have a common denominator. So then I have this right here, which is one rational expression, and I set it equal to 0 and solve. It's not that bad because if you multiply both sides by the denominator, it disappears on us. So now I have the numerator equal to 0. I need to isolate the 3x. I move it over. That's what I have here. And then I need to undo the square root. So I went ahead and squared both sides of the equation. Then if you notice from here, I'm just solving for x. I distributed my, remember negative 2 squared is 4, and then I have the radicand, so I distributed my 4 in, and then I just wanted to isolate the x's on one side, so I moved the bigger one over. I subtracted 9x from both sides, and then I subtracted 64 from both sides. I get this equation here, and then I keep solving for x. I see that I get x equals a positive and a negative and square root of 64 over 5. But remember, in this situation, I want to keep this x value positive. So I'm only going to use the principal root and simplifying it. I get 8 over the square root of 5. In order to test and find my minimization, I'm going to use the endpoints that we said was from 0 and 6. And this other critical point that I found. So I plug it into the original t function that I wrote, and I plug in the endpoints, and I see that I have the first at when x is 0, when x is 6, and when I plug in this critical point here, 8 divided by the square root of 5, it is approximately 3.49. It is my smallest value, so this is definitely the minimized point of where she wants to row to on the shoreline. From here, We want to go to part B. Part B says if she walks at 3 miles per hour, what is the minimum speed at which she must row so that the quickest way to the restaurant is to row directly with no walking? So from here, this one, I have the picture drawn again, but instead of some point at the shoreline, we are going right to the restaurant. So what they want us to do is we are going to cut out um, what we were plugging in for the rate of rowing, because now we want to know what speed would make this the fastest so we can get there quick. All right, so we're going to leave R in not as a variable, but as a representation for some constant number. That's what we're going to solve this equation for, is that R. So I go ahead, I take the derivative of the function again, and I want to set it equal to 0. But at some point, you've got to realize I've got an x and an r, and I want to solve for r. So I get to a point where maybe none of this I should be doing. I get to this point, and I say, okay, wait a minute. Before I move any further, so since I don't want this woman to walk at all, and we said, remember, we were from 0 to 6 here for our two spots, because I don't want her to walk at all, I'm going to plug in 6 for x. I'm going to plug in 6 for x. So then I'm going to go ahead and I have here 18 minus r squaring 6 is equal to 0. I want to solve for r now. I've got negative r times the square root of 52 is equal to negative 18. Divide through by negative square root of 52, and I get 18 equals. So I have 18 over the square root of 52. This does simplify down to 9 over the square root of 13. So she must now row at a speed of 9 divided by 13 miles per hour. And that is our answer for part B.